Principles of Bioproduct Separation, Module 13, Drying, Segment 1, Basic Concept. With me, Yusuf from School of Life Sciences and Technology, Institut Teknologi Bandung. In this module, we will discuss about basic concepts, drying equipment, conduction drying, and last but not least, adiabatic drying. At the end of this module, students will be assigned to do several exercises to determine wet bulb temperature, determine relative humidity, determine percentage of denaturation, determine air flow rate, determine drying time, determine evaporation time. By drying, we are referring to reduction of liquid content, either water or organic solvent, from an initial value to an acceptable value. Drying biological materials can serve several purposes. It can stabilize the bulk product until it can be formulated. It can preserve activity of, for example, enzymes in bacterial cells. It can recover expensive organic solvents. It is important to know three types of information in a drying process. First, we want to know how much water content in the solid, which is rooted in thermodynamics and solid-vapor equilibrium. Second, we want to know how fast this water will evaporate, which is a dynamic consequence of transport phenomena. Third, we want to know how fast our product will change or degrade, which is related to chemical reaction kinetics. Water in most biological materials is present in two forms, free water and bound water. Free water is that held in spaces between cells or in capillaries of porous precipitates. It has the same density, viscosity, heat capacity, and vapor pressure as bulk water. Free water can flow within solid materials and can be drawn by capillarity at the solid surface. Bulk water may exist within the solid in amounts exceeding free water, but its properties are different. It does not migrate easily and it has a higher heat of vaporization. Bound water has a lower vapor pressure than free water, which is different for biological materials. In most cases, we want to know how the water concentration in the vapor, which is in equilibrium with a particular water concentration in the solid. Such vapor-liquid equilibria are thermodynamic properties which must be obtained by experiment. They have a different form for free water and for bound water. For free water, the vapor-liquid equilibrium is commonly given as a psychometric chart, as shown in the right figure. This chart, valid for free water in all materials, gives the water concentration in the vapor plotted on the ordinate versus the temperature plotted on the abscissa. There are three important parameters that must be highlighted from the psychometric chart. First, the water concentration is not commonly expressed as moles water per volume gas or even as partial pressure, but as humidity. Humidity is defined as the mass of water per mass of dry air. Concentration, partial pressure, and humidity are closely related. They can be expressed by equation 1. The second parameter is relative humidity that can be defined in terms of partial pressure and humidity as shown in equation 2 and 3. The third special parameter is wet bulb temperature. The wet bulb temperature is the temperature read by a thermometer covered in water-soaked cloth over which air is passed. At 100% relative humidity, the wet bulb temperature is equal to the air temperature measured by a dry bulb thermometer. The dry bulb minus the wet bulb temperature is a measure of the humidity. In order to know how fast water evaporates from an object, the evaporation rate per area can be calculated using equation 4. The mass transfer coefficient is closely related to the diffusion coefficient as shown in equation 5. Because the evaporation rate is a function of the vapor pressure, it is also a function of temperature and hence of the rate of heating, which can be expressed as shown in equation 6. In some drying processes, equation 4 to equation 6 can be simplified as Reynolds analogy as shown in equation 7. The Reynolds analogy is accurate only for gases in turbulent flow, which is the common case for drying. There are three most common undesirable effects in drying, particularly case hardening, chemical dehydration, and protein denaturation. Case hardening occurs when the initial drying is so rapid that a shell of dried material is formed around a wet center. The shell is relatively impervious to moisture, so the drying essentially stops. Reducing the initial drying rate so that the shell does not form is the common cure to this problem. Chemical dehydration can be a problem with materials of any molecular weights. The water molecules are removed from the product molecules. This occurs largely as the result of excessive local heating and again can be avoided by drying more slowly. The most serious problem, protein denaturation, is a function of temperature, time, and water content. These factors are coupled. The denaturation follows first-order kinetics. Thus, the activity of protein versus time can be determined using equation 8 and equation 9. For the next segment, we will discuss about drying equipment. Until then, I am Yusuf from Institut Teknologi Bandung.